Hello, my name is John Ray Rao, and today I'm going to be presenting my final project for CpE 302. I made a game, and it's called Disco 9. So this is what I'll be going over today, but I wrote a little story just to help people understand what the game is. So because there's not really an easy way to compare it. So in Disco 9, the player is living it up on the disco floor. They have to remember their dance moves to make the white floor light up. However, they can only have 9 missteps before the floor turns off. The player must prove themselves as the best dancer by completing as many moves as they remember with the fewest mistakes and the fastest time. So the way that translate to the DE2 board is that players are presented with a 4x4 white grid, and underneath the white is a color. And so players can reveal the color by flipping a switch. So flipping A would flip this A, it would show you the color. I would show you the color underneath I. And so you're trying to match the colors because when they match, they stay on. You'll get a red light here indicating that those were matched. But if they don't match, then you lose a life. You lose one of your 9 lives. And when you lose all of them, you lose the game. So you have to be careful when you're matching to figure out which ones you're supposed to be matching. And you can figure that out by holding this key 3, which shows you the whole grid. But the thing is, when you press this, you can remember again what you're supposed to do, but you reset all your matches. So you have to remember the whole grid, not just portions of it. And an important thing to note is that in the upper half, there will always be a matching color in the lower half. But if the player wanted a different grid, they can actually restart the game and get a different one. It's going to be random, the colors and where they will match by pressing key 0. And like I said, there's a lives counter, and there's also a points counter. Whenever they get a whole match where all the colors light up, they get 1 point. But then it resets, and so they have to figure out again what's the new thing I have to memorize. And so they can also see how long they've been playing here. It displays minutes to seconds. And so I made a diagram just to help people understand. And so the first part of the diagram is the group 1. It's responsible for the random color ID and position generation. And so an important part of that is being able to store the values. So I figured that I could use a register file to do that, because a register file, given an address, it can load it at a specific register, or just one specific register. You could have this input D only at one of these. And so basically, you're able to get these arrays with these register files. And I use these numbers to represent, each number represents a color, and I just output the color if a number is, if the ID is a certain number. So that's how I get different results, by storing it in this register file. And these are randomized through these generators, which are basically LFSRs, which are linear feedback shift registers. And you can see that they have different, these 2 register files. The first one's the first upper half of the grid, and the second one's the lower half of the 4x4 grid. And they have different write addresses, but they have the same color ID because they need to have the same colors. You can't have an uneven amount of one color. Otherwise, you can't match the whole thing. And so yes, using this LFSR, you can get random IDs in random positions. But the thing is, it's not exactly random. LFSR is pseudo-random, because if you know the seed, it's actually deterministic. So what I did is this LFSR can also load a new seed, and this enable only occurs when when the player does something and their user input is random. So like pressing a button, you can't predict what will show up based on the button press. And also when they complete the grid, it resets. It gets a new seed. And so also the nice thing about this LFSR is not only that you can get different seeds and get different sequences, but the sequences have a special property such that before they repeat, they have a maximal length of 7. The 3 bits have a maximal length of 7. So it's going to produce 001 to 111 in a certain order. So for example, they're all loaded, they all start at 000 by default, and so For this is right address 1, this is right address 2, this is caller ID, so value 0 always gets loaded at address 0. And here, value 4 gets sent to address 1 and address 2. Value 2 is get sent to address 4 and address 5. And it goes on like this, so you could get a whole array. And just by changing the seed, you can make have different matches. So instead of 4 matching with 5, maybe it'll match with 7. So the whole thing, it'll be offset, and you'll get a whole new amount of matches. And you can also get different colors based on this table, where given a current seed, it produces a new one. And so it produces a new one through this control unit. And it sets 0 at first, and it seeds the LFSR. And at this state, it basically, the LFSR gets the opportunity to fill up the register file. And so it does that until it gets a new seed when the player wants one, when they press a key, or when they complete a new match. So they get a new, the LFSR gets new seeds, which get new values, which gets new positions and new colors. So this is how the LFSRs, the neat thing about them, they produce randomness and they can produce the values. Because as you see here, even if you get a new seed, you'll notice that they have the same, they're basically the same set of numbers. So all the colors will still output, and so they will all still contain matches, even though the matches are in different places. And theoretically, Disco 9 has 7 addresses times 7 addresses, 49 different match positions, and 249 different color grids that players can generate. So it's never like predictable. You can always get, as you see here, a different set of numbers that you have to memorize to match. And so group 2 uses the values, the color IDs from the register file to basically make a game. It's the game logic. And so the first important part is these conditions. So it needs to check if the sum, which is the switches, is adding all the switches, if it's equal to 2 or if it's equal to 0. And it uses that here when sum equals 0 equals 1. But basically, this color state, it feeds into the VGA output. And it outputs these bits. So it's one hot such that only one is on at a time, or none are. And it describes what's going to happen. For start black is 1, it's going to be, the grid's going to turn black. Turn white is 1, it's going to turn white. Show all is 1, it's going to show all the colors. And when it's accepting input, none of them are on. And so I've made it so that they only get on when there was a match or when you flip it up with a switch. And as you can see here, you can get to different positions based on different inputs. And when the game ends, it turns back. This game end is 1. And so the way that the matches occur, to figure out like a complete match, or even like to when an invalid match happens to decrement the lives counter, what it does basically is the register files, it has no read enable, so it's just outputting all 8 at once. And so what this module does is it takes it makes a switch as a read enable, and it ORs all of them such that in the upper half there's one ID, in the lower half there's one ID to compare to. So has matches is going to figure out if these are equal or not. And they're going to be equal by default even if the switches are off, because it's going to be 0, 0, 0 matching with 0, 0, 0. So you have to make sure that the sum is equal to 2 before that you have a valid match. And so this match vector has many bits that it gets sent to the VGA output to figure out which square should stay on. And so when there's a match and the switch was on, it should store a match, except if there's only one switch up, or if it's not accepting input, if it's showing all, if it's turning white. And it stays on when it is 1 with this OR. But the invalid match, it doesn't have to store anything. It just figures out when there's not a match and the sum was equal to 2, that means that invalid match is 1. And so when invalid match is 1, this lives counter decrements by 1. Basically that's what it's showing here. eventually when you run out of lives, you go to 0, the game ends. So, but when you press key 0 to reset the game, it always starts at 9 again. And so, using that game logic, you can actually get output so that the user knows what's happening. So, for example, the VGA output, this is basically showing the is row, these booleans. It's figuring out what position the square should be in, and how wide and long they should be. So, and they all get sent to this procedure display colors, which displays a color based on the color ID. And I just had to kind of experiment to figure out how to get these, what values of RGB would produce the colors I wanted. I figured that out here. And based on the outputs from the other modules, it does what it should. So, and then there's other outputs too. There's a point counter which increments whenever the complete match, when all the colors are lit up. When it's 1, it gets incremented by 1, and it keeps track of the 1's place and the 10's place, and increments by 10 when it goes from 9 to 0. And the timer also, it increments whenever there's a second, but it keeps track of the seconds, the 10 seconds, the minutes, and the 10 minutes. So it can go from 0 minutes to a whole hour. But if you press key 0, then it resets. But also with the point counter, when the game end is 1, it stops updating, just like with the timer. So basically, that's what basically is shown here. And this is just how calculate 1 second clock cycle. So I just demonstrate how it works. So of course it starts black, so you have to press the reset. And so I'm going to show all the colors by holding the button. And you can see which ones are matching: AI, BK, CO, DM. And whenever I restart it, it gets a new grid, so it's always random. And so what the player can decide to do is just hold the button to memorize which ones they need to memorize. And see, look, I made a mistake here, so it went from 9 to 8. But yeah, I made another mistake. So every time you make a mistake, you can run out of lives pretty quick. So you have to be careful. You have to really try to memorize which one is which. So eventually I do get the whole match, and I get a point. And so it's very convenient, and the timer's still going. But and you see here also, the matches, when it gets smashed, it lights up here. But when you hold this, it resets. So just like I intended it to. So I lose the game, so the timer stops updating, and it says I had 1 point in 1 minute and 51. But then I can reset, and I can play the game again, get a different grid. So that was basically that's the gist of Disco 9. And I just wanted to acknowledge Professor Salvaraj, because he taught me how to look at VHDL code as like a hardware language instead of just a software language. And also the flashcard game developers, because I got inspiration from them. I thought this was a really fruitful and fun project.